enzymes and probiotic behavior. This applies to a lot of proteins and enzymes and medicine. So isomerism, the idea of isomers are compounds that contain the same number of carbon, hydrogen, oxygen, etc. So here's a 1, 2, 3, 4, 5. This is a, if I just take this metal and put it here, this molecule still contains 6 carbons. Still contains the same number of hydrogens, 14, but it's connected differently. When you connect them differently, and they actually come up with different names, these are known as constitutional. I'll exaggerate this a little bit. This is cyclohexane. Doesn't matter what these are. I know we've been doing this for a while now, so you put it doesn't matter what these are. If I tell you what's the name of these, right? So first, we gotta name these. It's a cyclohexane, these are substituents. It doesn't matter what these are. This is 1, this is 2. Or this is 1, this is 2. If I move this here, it still contains the same thing, but this is 1, this is, that is a different name, right? 1, 2 is different than 1. So anytime you move molecules around, or you move parts of the molecule around, and maintain everything else the same, it's called a constitutional. So everything else remains the same number of carbon, hydrogen, etc., and you move parts of the molecule and you end up with a different name. That is by definition a constitutional. Everything else, actually that's good news. Everything else is a type of a stereoisomer. What's an example of stereoisomer? I want to give you an example of something that you've already seen. I don't want to give you something that's weird and all that stuff you haven't seen. I'll give you one. I'm going back to the structure. Where are these located? 1, 2, right? So whatever this is, and again, use your imagination, this is on carbon 1, this is on carbon 2. They both pointed up. So this is cis 1, 2, right? This is cis 1, 2. If I just take this and move it here, it's still 1, but this is not cis. That's an example of it's not constitutional because they're connected to the same carbons. Constitutional, they'll be connected to different carbons, right? If I make it 1, 2 versus 1, 3, that's a different carbon altogether. They still on carbon 1 and 2. I did not change the position, but I changed it from cis to, that's a type of a stereoisomer. So that again, there are more complicated ones, but I wanted to start with something that you've seen before. So constitutional isomers are made up of the same, everything the same, but they have different names because there'll be 1, 2, or 1, 3, 1, 4, etc. Whereas stereoisomers have the same order. Whether it's from carbon 1, carbon 2, everything is the same, but they're not the same molecule, so there's something about them that makes them different. And so, first type of stereoisomer is cis and trans, right? It's a type of a stereoisomer. Not today, and probably not tomorrow, probably not to the exam. You will learn these have a name. Some people call them cis trans, which is fine, because it's actually true. If I ask an exam, what is the relationship, and you say cis trans, actually, that is true. They have a name. Cis trans are called diastereotypes. Don't write this down. This is coming up next week. And so the point is, there are molecules that have the same name, 1, 2 dimethylcyclohexane, 1, 2 dimethylcyclohexane. However, in one case, the two metals are pointed up, and the other one is up, one is down. And so this is a type of a stereoisomers. that's why we say cis and trans to differentiate between the two. You could also have cis and trans when you have alkenes. I want to show you. So, unlike alkanes, so I'm going to show you. So this is an alkane. Cis, trans. Cis, trans. You agree? No, why not? This is the same molecule, it's just rotating. Right? It's, can I do this rotation with a ring? No, because the ring is closed. So cis and trans are molecules where you cannot go back and forth between cis and trans. Right? In a ring, cis will always remain as cis, and trans will always remain as trans. Whereas what I just did here was like a magic trick. I said both cis and no, this is the same. These are different formulas, right? That was, we talked about that last week. So, in order to have cis and trans, you must have a ring, right? And I'm going to show you, if we have a ring, right? Trans, right? Trans. Still, no matter what I do, it's always going to be trans, right? Because it's not, so trans always remains as trans, cis remains as cis. So in order to have cis and trans, you must have something that prevents it from rotating. You know what else prevents things from rotating? Somebody wants, I can pass this around, you can try it. This is a alkene, double bond. You can't rotate around an alkene. It's stuck. So that means if I put these on the same side and I can't rotate, that means they are stuck in the same position. So that's a cis. Cis means on the same side. Now when we did cyclohexanes, we said both pointed up or both pointed down, right? That's cis. And when they are on opposite sides, that's a trans, right? Again, one up, one. Doesn't matter which one. So you could have a cis trans when you have an alkene because you cannot rotate around an alkene, or you have a ring. And so cis trans, what kind of isomers are they? They are stereoisomers, right? No, diastereoisomers is the exact name, but they're a type of a stereoisomers called cis and trans. All right, what's the issue between these two? I'm going to show you. Tell me the relationship between this molecule, the magic trick, and this molecule. They are the same, right? It's not like if I asked you to draw that alcohol, right? The two chairs, remember the two chairs refer to the same molecule. So these are different conformers, same molecule. How about here? All right, so what we do is, this OH, up or down? This OH, up. This is up and up. This OH, up. This OH, up and up, down, we call them. That's the type of a. What are these? Before you jump to conclusion, count. How many carbons we have here? 4. 1, 2, 3. How many hydrogens? 2, 4, 6. 8. How many hydrogens? 3, 4, 5, 8. And 1 oxygen. Are the number of hydrogen, oxygen, carbon, etc. the same? Yes. Now, but are these related by the way? No, this is an ether, that's a ketone. What do we call these? Constitutional isomers. All right, how about this one? How about that one? Why identical? Because it's the same. I'm building it. Thank you. I'm building it, and I want to show you. That's why I remember first I said that biotech would. Look, the first one is this. Two metals metal up, right? The second one.
It's the same thing.
This is the same
thing.
How about these?
Those are.
So I'm gonna build it, right? So we have an ethyl, the first one.
That's the.
And I want to show you, actually, Carol teach you a trick for these.
No, isn't it?
What you do is when you have an alkene, draw a line through the alkene and see where the substituents are. Are these two substituents on the same side or opposite side of the plane?
Opposite.
Opposite. That makes it a trans. How about, okay, same thing. Are these two substituents on the same side or opposite side?
Same side.
Okay, so this is a cis. So that's a cis trans, and cis trans are a type of a filler. So identical, stereoisomers, constitutional stereoisomers. All right, let's think about in terms of cis and trans. This, what do you do when you have a double bond? Draw a line through the double bond. Are these two on the same or opposite side? Where is this pointed, up or down? Up? Oh, by the way, so same is cis. Up and up is? Up and down is? Trans. How about this one? Trans. How about this? Good. Neither. Because it's the same, it's these two groups are the same. You have to have something different to make this cis and trans. So cis, trans. Okay, now? What? And so the next topic we're going to talk about has to do with probably the most important concept in this chapter. I'm not going to talk about it. I'm not going to introduce all the details, but I want to kind of tell you about it. And I want to tell you what is the idea of chirality and what it means. Now, if you chiral molecules are molecules that look exactly the same. Everything about them looks the same, but they're not. What? Now, my right and left hand are made up, look exactly the same, right? They have the same kind of fingers, everything looks the same, but they're not the same, right? Try to put your right hand glove in your left hand. Would it fit? How could it not fit? They look the same, right? Try shaking hands with my right hand and her left hand. It wouldn't work. Why not? Both hands they're not the same. By the way, car. We drive, in the US, our seat is on this side, right? If you go to England or some other place in the world where they have on the other side, have you ever tried driving on the opposite side? Anybody has tried it? Because I have. Yeah, I was in Tanzania and I rented a car when I'm eating. And they gave me the car and I opened the door and I'm on the passenger side. I'm like, what do I do? And I was like, I couldn't drive. I mean, it wasn't easy. It looks exactly the same. Got it? So this concept is extremely important. Which has to do with chirality. So chirality is not about cis-trans molecule, that's one type. A chiral molecule is a molecule that is asymmetric. Right? It's asymmetric and the idea of not superimposable. Now what does that mean? If I take my right hand, even though they look the same, if I try to superimpose them, guess what? It wouldn't work out. No matter what I do, they don't work out, right? And so that's the idea of chirality. And I'll build the mountain for it. Sorry, give me a second. Blue and red and a metal. All right, here we go. So blue. Red. All right, so if you look at these two molecules, right? Red, blue, and whatever this metal is, right? So they look kind of the same, but they're like my hands. No matter what I do, if I try to superimpose them, they're not superimposable. So the red and the blue, the metal and metal matches, but not this. What if I do this? Well, I can actually do. I'm smart. All right, look. Now the blue and the blue matches, but no matter what you do, it wouldn't. So that makes them, they're not, they look the same, right? By the way, if you want to name them, they have exactly the same names. It's right hand and left hand, right? It's a hand, right? It's the same. They have the same name, but and guess what? We're going to give them a name just like this because this is a hand, but to be specific, we say right hand. And so we're going to give them the same name, but then we're going to give them a kind of right hand, left hand notation to differentiate. And that is the topic that we're going to be talking about in the next chapter. I'll tell you, this is crap, obviously. It's important for, I did mention, for biology, for medicine, and just to let you know, most of the drug you take has a chirality center. Just to let you know, like proteins and enzymes, the way they work, they have proteins and enzymes and medicine, they have right and left. And so when they go to shake hands with another protein or enzyme, if the right and right hand don't shake properly, there's no reaction. And that's why, they say that if you study biology, they say, well, this protein can enter the cell because of selective. It's not selective. It means a protein that they both have the same proper orientation and they can kind of fit together. That makes it. Well, I did say when we started that if you have a handheld building device, that would be. Just a reminder, our exam is on